So if I hear that, that's like, oh, fuck. So a rectangle has its lower left vertex at the origin. And its upper right vertex on the graph of y equals 4 minus x over 2 plus x. Find the largest possible area of such a rectangle. Now, obviously, you're going to work on this yourself, obviously. But before we do that, let's look back at the previous problem, or you look back at the previous problem, and can we maybe make a little outline of what you're supposed to do? Like, what do we think? So what would be like your first steps for this? Who wants to say? Obviously, you can look back at the previous example. What are the first things you have to do here? Okay, so let's see. So Sarah says, get the objective. Kai says, draw it out. Dina says, get the objective and the constraint. Okay, so let's say, so let's put like any, you may not necessarily, not all problems will need a diagram. So let's say, let's put Kai's thing, diagrams. Let's put that at the start because, sometimes you need them, sometimes you don't. Let's say then Sarah says, I get the objective function. Okay, good. And then Dina said, get the constraint equation. Okay, good. So now what would you do after that? Once you have your objective and your constraint, what would you do after that?
Critical points?
Not quite. Critical points happen a little bit later. There's kind of something in between. So let's see. Dina says, substitute the constraint. That's right. So I'm going to say, get your one variable objective, right? Remember, we use the constraint equation to eliminate one of the variables. So I'm going to say one variable objective. And then who said critical points? Was that Caitlin? So then Caitlin, you're right. So then the next thing I would do is, or actually not quite just yet, there's something else, but maybe it might be a little bit subtle. You also need to identify the interval of interest, right? Because you need to say, I want to maximize or minimize this function on this interval. So make sure you get the interval of interest. That's sometimes forgotten a lot by students. Then you can get the critical points. And then after I get my critical points, what do I do after that? So Kai says sign chart. Emily says verify. Okay, so I'm just going to say verify the minimum or max exists. Because you can do that in actually a few ways, not necessarily a sign chart for the first derivative. So verify the min or max exists, and then finally answer the question. Okay, so now I'm going to give you a few minutes to actually work on this. But that's kind of a very rough, that's a good rough sketch of how to actually do this problem. So very good work. So I'm going to give you 5.5 minutes. You may not get all the steps. That's fine. Try to get as many as you can.
For the last example, you said that like there's no absolute maximum, but it's also arbitrarily large. So is it both answers then?
So like I said, having no maximum is not the same as saying the values of the function go off to infinity. So like I said, you can have a function that kind of just approaches, say like y equals 1 from below. There's no maximum to this function, but the values don't go off to infinity. Okay. In the previous example, we had both no absolute maximum and the function values going off to infinity. Okay. All right, that's it. Time's up. So we have a good roadmap. Let me delete it. It's gone. Okay, so we said draw a diagram first. Well, did you draw a diagram? Did anyone look at a graphing calculator to at least see what this graph looks like? Does it really matter? Karen, you said no. Does it matter?
No, I don't think so. Because it.
Yeah, not really. Yeah. I mean, it might matter where the asymptotes are, but for all you know, for all you care about, the graph kind of looks like this. That's really all that matters. It doesn't look like that. It looks like this. But let's actually use I'll use an accurate depiction of the graph, but it really doesn't matter, to be honest. And we'll see why. Okay, so where's this rectangle? So it says the lower left vertex is at the origin, and the upper right vertex is on the graph somewhere. So there's the upper right vertex. So the reason why I'm saying the shape of this graph doesn't really matter is because that's really all you need to know. You just need to know that we have some rectangle in the first quadrant and that the upper right vertex is on that graph. That's it. Okay, so that's my diagram. What would be your, so let's say, so what variables do you want to introduce here? You might say X and Y. I really don't like X and Y. I'm going to call it W and H. So let's let W and H be the width and the height. Okay, what is our objective function in terms of W and H? We want to do what? Do I want to minimize something? Do I want to maximize something? And then what is that function? Okay, so we want to maximize this, right? It said what? You're always looking for those superlatives, right? Largest, fastest, smallest, cheapest. So largest means I want to maximize the area. So I want to find the largest possible area. So we want to maximize the function, and Karen tells us it's just the function W times H. So we'll call that A for area. And that is the objective. Subject to what constraint? Right? Because we said that was next on our roadmap, right? When I've identified the function I want to maximize, but it's a two-variable function. So I need a constraint equation to help me eliminate that variable. So who wants to tell me what the constraint is? You all worked on it for 5.5 minutes.
Since we're working with W and H, would it be H equals 4 minus W divided by 2 plus W?
Okay, so you said it was H equals whatever that expression was, right? But with W. So that's actually correct. Oops. Constraint. Right? So if you're not clear about how we got that constraint, notice that I told you that the upper right vertex has to lie on this graph, right? Now, what are the coordinates of this point right here? The coordinates of the upper right vertex, so the lower left vertex is obviously 0, 0. The upper right vertex has coordinates WH, right? Because W is the horizontal and H is the vertical. But if WH is supposed to lie on the graph of that function, that means, well, H is playing the role of Y and W is playing the role of X. So H must equal 4 minus W over 2 plus W, right? Okay, so now we can actually write down So now I have my objective in 2 variables. I have my constraint. So now I can use my constraint to write my objective in terms of 1 variable. Okay. So that means I'm looking at the function. It's going to be just a function of w, and it's w times h. So it's just going to be w times 4 minus w over 2 plus w, right? I just multiplied w and h. That's it. What is our interval of interest? Zero to 4? Is that correct? Kai says it's 0 to 4. 0 to infinity? Uh-oh, didn't we have this discussion last time? Alex and Kai are disagreeing with each other. That's not good, because now everyone else doesn't know what to say. Uh-oh. Does anyone else have another idea? What about 0 to 4, not including the endpoints? What about 0 to infinity, including the endpoint? Sapir, what did you say for the interval of interest? Maybe not sure?
I'm not sure anymore.
Not sure anymore, but what did you say initially?
I thought that it's 0 to infinity, but now I'm not sure.
I'm going to be completely honest with you. I'm very lost. Well, what's your question? What are you lost about? What's your question? Where did we lose you, Julia?
I don't know. I guess I don't know. Everything's just confusing. I don't have like a specific question. It's just like the
Well,
whole.
to do like a 20-second recap of this question. So we're given a rectangle that's described to us like this, right? Lower left vertex at the origin, upper right vertex on the graph. The thing I want to maximize is the area, because the question told me find the largest possible area. So that's just w times h in this case. However, this is a 2-variable function. I need a constraint equation that lets me eliminate one of the variables in terms of the other one. I noticed that this point, the upper right vertex, is just wh. But that has to lie on the graph, right? So that means h must be 4 minus w over 2 plus w, right? Because that's the equation of the graph. Y equals whatever, right? Y equals 4 minus x over 2 plus x. So that means my area function can be written in terms of 1 variable only, like this. So that's where we are right now. Now we're discussing, I have my objective function. I know I'm going to just find the derivative of this at it equal to 0, find the critical points, right? I know what I'm going to do afterwards, but I need to know what interval I'm maximizing this on. And that actually is important for this function. Now, Kai says you can't have a negative y on a rectangle. Okay, so that's actually good to realize here. For our interval of interest, Kai notices, well, w cannot be negative and h can't be negative either. So let's get rid of all these things. So for our interval of interest, so Kai said both of these things, I have a W and I have an H, and they are not allowed to be negative, right? Because they're lengths, right? Does everyone, Emily, do you agree with that? That W and H can't be negative? Do you?
Sure. I
Sure?
don't know, if you want me to be honest.
You're not sure? Okay. Well, what would it, first of all, what would it look like? Go ahead.
I would say yeah, if they're both in the first quadrant. So
That's right. So part of the problem told me that the lower left vertex is at the origin. So that means the upper right vertex has to be obviously to the right. In other words, this W has to be, it can't be negative, right? Because otherwise my rectangle, if my rectangle would look like this, then that means the lower right vertex would be the origin, not the lower left vertex, or it'd be the opposite orientation. So my W is obviously not allowed to be negative. Can my W be 0? Is that allowed? Can W actually be equal to 0? That's actually a good question. You don't think so? Well, Kai, you actually did think so because you told me 0 to 4, including both endpoints. So I guess you're changing your story now.
Yes, because like there's no like definitive like endpoints given.
Well, the endpoints were not given to you explicitly, but they are described to you. There is kind of these hidden constraints. Again, the fact that the upper right vertex has to be on the graph. For instance, my rectangle cannot dip below the x-axis, right? I can't have a rectangle that looks like this, right? Because then the upper left would be the origin, not the lower left. So there is a range, there is a limitation to how big W can be. Now, Tulip says it wouldn't be a rectangle then. So I'm actually going to tell you that W equals 0 is allowed. And so is H equals 0. So I want to make clear of this. So lengths can be 0 if no constraint is violated. Now you might say it might be a you might say it's not a rectangle, but actually it is. So what does a rectangle with width 0 look like? It looks like a line segment. So that is a rectangle. It just has length 0. That's all. So they're called degenerate cases. It's called a degenerate rectangle because one of the dimensions has collapsed to 0. It's not because they're on 4chan all day.
Does that say violated?
Violated, yes. So W equals 0 is actually okay. In fact, W equals 0 would correspond to what? W equals 0 would be a rectangle, or actually a line segment that looks like this. It's just on the y-axis. The area is 0. That's perfectly fine. Now, the other extreme would be if H equals 0 and I have a rectangle that goes all the way like this. That would be the other extreme. Now, what does that correspond to? If H equals 0, what does that correspond to in terms of W? That's actually W equals 4. And how do I know that? I just set H equal to 0, right? I just look for that y-intercept. Or sorry, the x-intercept of the graph. So H equals 0 and W equals 0 are the two extreme cases, and they actually are both allowed. Okay, now that is a very subtle point. So I don't want you to think because we spent like 10 minutes on that point that it's a very, very important point. It's not that important, but including the endpoints is actually really nice because remember, if the endpoints can be included, that makes your job easier, right? Because we learned from 4.1 that if you find the critical points and the values at the two endpoints, you just compare them, and the smallest is the min, the biggest is the max, right? Remember, if you're on a closed and bounded interval, the min and max are guaranteed to exist, and you can skip that verification process. So that's why including the endpoints, if possible, is actually always a good idea for you. If you don't want to include the endpoints, if you just want to say, I can only go from 0 to 4, not including the endpoints, then you still must do that verification procedure because open interval not guaranteed to exist, right? The mins and maxes. Okay, so let's write down our goal now. So our goal we want to find, what do we want to find? It was the largest area. Find the absolute minimum, absolute maximum of my area function, which was this thing. Right? Yeah, that's my area function on the interval 0, 4. Now, again, to be clear, W equals 0 gives me a rectangle that's just a vertical line segment, and H equals 0, which is the same thing as W equals 4, gives me a horizontal line segment. And both of those are okay. right? It's okay to have line segments as rectangles. Jan, what are you thinking? Questions? Okay. Now, where do we go from here? Now this is the calculus portion, and hopefully everyone should know how to go from here, right? If you want to find the maximum of a function on an interval, just find the critical points and then go from there, right? Any questions so far about the first part of this problem? Like I said, even though it's technically a non-calculus portion of the problem, it's still pretty tricky, right? It's still not the easiest thing in the world. Because you're interpreting English words into math, right? It's tricky sometimes. Okay, so let's get the derivative of this. I would recommend just multiplying this out for 4w minus w squared over 2 plus w, and then using quotient rule. So that's what I would suggest for that instead of using product rule and all that. So after I get my derivative and simplify it, my derivative ends up being 8 minus 4w minus w squared over 2 plus w squared. I set it equal to 0. I have to use quadratic formula, right? If I set this equal to 0, I set the numerator equal to 0, and I need to use quadratic formula on the top. So I get two possibilities. I get w equals -2 minus 2 root 3, or w equals -2 plus 2 root 3. So that's quadratic formula. All right, so hopefully I don't have to go over all the algebra with you guys. Now, one of these critical points is not allowed. Jitesh, wake up. I think Jitesh is actually kind of frozen and lagging. Okay, so we won't call him Jitesh. Nishika.
I'm awake. It's just that my screen is lagging like crazy.
Yeah, it is. Okay, so let me ask Nishika then.
All right.
All right, so Nishika, one of these critical numbers is not allowed. Which one is it, very quickly?
-2 minus 2 root 3.
Yeah, because that's a negative number, so it's not allowed. Yeah, exactly. The other one you can check is actually in the interval. It's somewhere in the interval. You can check that. Okay, so now what do we do? So normally for a normal optimization problem, we would say, okay, now we have to verify that the min and max exist. Alex, how do we know that the min and max already exists?
How do we know they exist?
Yeah, how do we know that the min and max already exists and I don't really need to do that verification?
Because of the interval closed and bounded.
Good, the interval is closed and bounded. Okay, good. So since f is continuous, specifically on this interval, it's not continuous for all numbers, but since f is continuous on 0, 4, and 0, 4 is closed and bounded, we know the min and max must exist. So we make a table of values. All right, once you know the min and max exists, you just need to make a table of values. All right, my x values were 0, 4, and this ridiculous number, -2 plus 2 root 3. And my y values are whatever this function is, right? 4, what was it? Sorry, they're actually not x values, they're w values. W times 4 minus w over 2 plus w, right? That was the original function. However, 0 obviously gives me 0, right? It was a vertical line segment, and 4 gives me 0, right? It's the horizontal line segment, 0 area. And this number you can check obviously gives you a positive number. I don't even care what the number is. I just know it's positive. So when you compare these three numbers, obviously the minimum is 0 and the maximum is whatever that number is. So the number, our critical number we found, that does give us the maximum. And that's it.
Would a sign chart not work for this? Or
It would, but you don't need to use it because our interval is closed and bounded, so we don't need to use it. If you want to use a sign chart, that's perfectly fine. You would find what? You would find, whoops, you would get one critical point, right? Like 0 to 4. I'd find one critical point, and you should find increasing and then decreasing, right? So sign chart is perfectly acceptable. I'm just saying you don't even have to bother with that because we were already including the 2 endpoints. So I'm just trying to show you kind of multiple ways of going about solving the problem. So the maximum area is whatever this is, f of -2 plus 2 root 3. So if you really want to get a simplified version of what that number is, it doesn't really matter. You can just use a calculator. It's 8 minus 4 root 3. But you can just use a calculator to get it to like 3 decimal places or something.